All right. So today we're going to start at magnetic boundary conditions. The conditions of the magnetic field exist at the boundary of two media. When the magnetic field passes from one medium to another, are called boundary conditions. All right, let me call about because I teach now. Okay, thanks. Sure, magnetic fields are simply magnetic boundary condition. When we consider magnetic boundary condition, the condition of the B field and the H field are studied at the boundary. The boundary between two different magnetic material is considered. To study condition of B and H at the boundary, both the vectors are resolved into two components, just like we did in the electrostatic field. The tangential to the boundary and the normal to the boundary. So consider a boundary between two isotopic, homogeneous, linear materials with different permeabilities, mu1 and mu2, as shown in figure 8.1.4. So, this is your medium 1, this is your medium 2. This is your boundary. First, we're going to deal with the normal component. So here, we resolve the magnetic field in the normal component and the tangential component. All right? Normal component, tangential component. So we're going to first consider the normal component. To find the normal component of B, select a closed Gaussian surface in the form of a right circular cylinder as shown in the figure. So this is a circular cylinder. Let the height of the cylinder be delta H. Delta H. And be placed in such a way that half is in medium 1 and half is in medium 2. Also, the axis of the cylinder is in the normal direction to the surface. So according to Gauss's law, B dot ds, the integral of B dot ds over the closed part is equal to 0. The surface integral must be evaluated over the surface, over the three surfaces. So over the closed surface, we're gonna evaluate the surface integral, top, bottom, and the side or lateral um, position. So over the closed surface, the three areas that we are looking at is B dot ds at the top, at the bottom, and over the side. But we are very much interested in the boundary. So we're gonna shrink this cylinder. So we're gonna squeeze this pillbox equally on both sides. Now, as we squeeze it towards the interface between medium 1 and medium 2, that means delta H go to 0. The cylinder tends to boundary and only the top and bottom surfaces contribute to the surface integral because delta H go to 0. So when you do the area around the side, because delta H is so small, it's almost 0. So all we are left with is the top and the bottom. Now, let the magnitude of normal component be normal, be N1 and be N2 in medium 1 and 2 respectively. As both the surfaces are very small, we can assume B normal 1 and B normal 2 constant over their surfaces. Hence, we can write for top B dot ds is the integral B normal 1 ds or B normal 1 delta S. And the similar thing for the bottom. Of course, we already agreed that for the side it's equal to 0. So from this equation up here, from this equation, this go to 0. We are left with this. Question is of the sign. Know that the negative sign is used for one of the surface integrals because normal component in medium 2 is entering the surface while medium 1 component is leaving the surface. What that means, if we go back to this, if the magnetic field is going this way, that means this would be entering the surface and this would be leaving the surface. So one is negative, one is positive. So if we cancel the delta S, this equation becomes this, or B normal 1 equal B normal 2. So in English, what that means is that the normal component of B is continuous at the boundary. Now, B is mu H. So if we make the substitution into this for mu1 H1 and mu2 H2, we end up with this. So in English, that is saying that the normal component of the H field is not continuous at the boundary. Okay. Now let us look at the tangential component. From Ampere's circuit law, the integral around the closed surface, the closed loop of H dot dl equal I. So here, let us select this closed surface. One, from A to B, LB. From A to B to C to D, back to A. So this is your closed loop. So we say the integral of H dot dl is equal to the current enclosed. So consider the closed loop that I just show you, A, B, C, D, back to A. So H dot dl would be H dot dl from A to B, H dot dl from B to 1, which is the boundary, H dot dl from 1 to C, H dot dl from C to D, from D to 2, and 2 back to A. A to B, B to 2, 2 to C, C to D, D to 1, 1 to A. Okay, they go the other way, but that's no problem. So from the figure, it is clear that the closed path is placed in such a way that its two sides, A and B and C and D, are parallel to the tangential direction to the surface, while the other two sides are normal to the surface at the boundary. So this closed path is placed in such a way that half of its position is in medium 1 and the remaining is in medium 2. The rectangular part is the rectangular path is an elementary rectangular path with elementary height delta H and elementary width delta W. So over small delta W, H can be assumed to be constant. Say H tangential 1 in medium 2 and H tangential 2 in medium 2, medium 1 and medium 2. Similar over small height, delta H over 2, H can be assumed to be constant. So H normal 1 in medium 1 and H normal 2 in medium 2. Now assume that K is the surface current normal to the path. Okay. All right, that kind of self-explanatory. So let's look. So Ellen, can you hold it down, please? Hello? Good God Almighty. We're gonna K, we're gonna substitute K for surface current for I. So K dot DL, which is K dot DW, equal H tangential 1 delta W plus H normal 1 delta H over 2 plus H normal 2 delta H over 2 minus H tangential 2 delta W minus H normal 1 delta H over 2 minus. You follow this equation?
Somewhat.
Tell me what you have. Tell me what.
All right. You see, sir, I was thinking about from the when we were doing electrostatic fields. So and I know it would be similar to that. So what I don't fully understand, like, or I lost track, maybe is a better way to say it, of when they put substituting things, I know it will come out as something similar to the electrostatic fields.
No, say that again, Mr. Donga.
All right, so with this now, I'm not completely, I never followed all of the substitutions, and I get the general concept of it, the path, the rectangular path and all of that. I know it will get a similar answer to like when we're doing electrostatic fields. So even though I don't follow this part specifically, I know that it will be H tangential to continuous at the boundary.
We'll go to the figure and see if we can shed some light. Remember, we say H dot DL would be from here to here, 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 right?
Yes, sir.
So we really shrink this down. And remember now, this would be, if this is positive, this is negative, right?
Yes, sir.
So H dot DL. Now I dot DL, we change, since it's a surface, we change I to K. So that's how that change. So if we put in the so A tangential 1 would be up top there. That there, which would be delta W.
H normal 1, H normal 2. And that will be negative over there, the H tangential 2, because that is in the mat, like it is.
So this, if we just look at the top, this, you're gonna end up, when you go to 2, you're gonna end up with the negative, right?
Yes, sir.
And this is coming down to the surface, so you're gonna end up now with a negative for that too. And this, do nothing with a negative here.
Okay. Let's just simplify. Okay.
So as we shrink it and delta H go to 0. So as delta H go to 0, this go, this go, this go, this go. So we just left with this and this. So this So this statement is very, very profound. In vector form, we can express both relation by a cross product as this. So the special case is when there is no current at the boundary. So K becomes 0. If K becomes 0, H tangential 1 equal H tangential 2. But remember, B equal mu H. So if we substitute the mu, the B for H, we end up with this.